Hopefully you've had a chance to try these practice problems. I've got about 5 I'm going to work through right now in this video. So we're going to start with 8. And it's asking, is chlorine paramagnetic or diamagnetic? And so a question like this is really asking us, does it have unpaired electrons or not? So I'm going to draw up a quick orbital diagram. I'm just going to make it degenerate since I don't really need to worry about the relative energy levels. So I know I'm going to have a 1s orbital, 2s, 2p, 3s. Oh, sorry. And 3p. And so going in and filling these electrons, chlorine has 17 total electrons. So I'll come in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So looking at this, I can see that I have 1 unpaired electron. So I will call chlorine paramagnetic. If it had no unpaired electrons, then I would call it diamagnetic. Okay, number 9. Refer to that image in our lectures of the atomic radii. Why do transition metals in general show very little variation in radius across each row? When you look at that picture, the transition metal sizes look really, really similar. And so thinking through this and thinking about size, that it really changes with effective nuclear charge. So as the effective nuclear charge increases, our size decreases for a row, right? And so it's really changing there as this increases is the increasing number of protons in our core, or sorry, in our nucleus compared to our valence electrons. Because it's those valence electrons that really dictate the size of the atom. So when we're in our transition metals, we're increasing our nuclear charge by +1, but we are not increasing our valence electrons. So the electrons are being added to the core electrons. Therefore, they're contributing to the shielding experienced by the valence. And so our Z effective isn't really changing as we go across the transition metals. That Z effective, remember, is equal to Z minus S. And so as this is increasing, so is our S, our core electrons. And so we get the same effective nuclear charge for our valence electrons across the transition metals for the most part. Okay, number 10, which of the following will be the largest atom? Support your answer by comparing effective nuclear charges. All right, so we are looking at arsenic, barium, and bismuth. And so I can take my periodic trend in general. Remember, we'll see that our size increases as we go down and over on our periodic table. And so just from that alone, I would predict that barium would have a larger size, or sorry, maybe it's bismuth. I don't have a periodic table in front of me. All right, so our barium is in, so pull up a periodic table if you've got one in front of you. Barium is in row 6, and our bismuth is also in row 6. So I would predict that barium would have the larger size. So I'm just going to underline it so I remember that. All right, so let's figure out the effective nuclear charges for these. So remember, that's going to be Z effective is equal to the atomic number minus the number of core electrons. So for arsenic, arsenic is in row 4. It has 33 core electrons, or sorry, 33 total electrons, and it has, for core electrons, 28. And so that's going to be the electrons in the n equals 1, n equals 2, and n equals 3 shells. And so that 28 is coming from the n equals 1 has 2 electrons, n equals 2 has 8 electrons, and our n equals 3 has 18 electrons. And I'm taking the sum of that to get to my 28. And so it's going to have an effective nuclear charge of +5. Now, for barium, it has a total number of electrons of 56. And counting up its core electrons in the same way, I'm going to have 54. And so that's going to equal a +2 effective nuclear charge. Now, for bismuth, it has a total of 83, but it has 64 core electrons. And so that's going to give me an effective nuclear charge of 19. So barium is going to be the largest atom because it has the smallest effective nuclear charge, and so it will have the least amount of pull on those valence electrons, and so they'll be able to be furthest away from the atom. And so our barium will be, oh, supposed to highlight, our barium will be our largest one. All right, now looking at the bottom, we're going to say which of the following will have, or sorry, 11, which will have the highest ionization energy and the lowest electron affinity. And so those should correlate together, right? If you have a really high ionization energy, it's going to be really hard to remove an electron. All right, so now turning to number 11, which of the following will have the highest ionization energy and the lowest electron affinity? And now these trends are pretty parallel. So up here in this upper right-hand corner, we have very high ionization energies. It's hard to remove an electron, and we have high electron affinities. It's easy to gain an electron. And down here at the bottom of our periodic table, we have low ionization energies and low electron affinities. And so looking at where these are all placed in our periodic table, we have, here I'm going to just highlight, make little. So our aluminum is kind of, it's about right here-ish. And our sulfur is in the same row, but closer to the noble gases. And then our polonium right here is further down our periodic table. It's right below sulfur, but lower down. And our thallium is right underneath our aluminum, but again, in the same row as that polonium. And so we're really looking at this grid of elements and trying to decide which is highest and which one's lowest for ionization energy and electron affinity. And so that means that our highest ionization energy is going to be the one that is in that's going to be in our upper right-hand corner. So that's going to be sulfur. So sulfur is going to have our highest ionization energy. And I'm looking at the one that is the smallest and yet closest to a noble gas. So then thinking about our lowest electron affinity, so a low electron affinity is going to correspond to the bottom left-hand corner. So I'm going to take this bottom left-hand corner one, which is our thallium. And so this will have our lowest electron affinity. So it's the least likely to release energy by gaining an electron. All right, so number 12. Use electron affinity and ionization energy to explain why metals tend to be oxidized while non-metals tend to be reduced. All right, so for this one, again, this comes back to ionization energy and electron affinity, because if something is ionized, it loses an electron. So let's write this out. So when something is ionized, it loses an electron, right? And so losing an electron is just oxidation. And then when something has a high electron affinity, it's energetically favorable to gain an electron, and so it's likely that they're going to be reduced. And so we will say that something is reduced when it has a high electron affinity, and something is easily oxidized when it has a low ionization energy, when it's easy to do it. So that means that low ionization energy, remember, That's down here in the lower right-hand corner. And so that's where our metals are. So this is our lower left-hand corner. So this is my kind of a periodic table. Whereas our higher electron affinities, sorry, not a great periodic table. Our electron affinity increases. Those are going to be our elements that are in our high upper right-hand corner. And that corresponds to our nonmetals. And our metallic character increases as we go down the periodic table and to the left. And so these are going to be our metals.